Greetings everyone, and welcome to our last section in Stat157, which is I'm going to merge section 6.1 and 6.2 together, and this is all about confidence intervals. So before we go there, let's back up and remind ourselves that statistical inference is the set of procedures that allow you to make predictions or estimates about populations based on samples. So for context, let's imagine that the Globe and Mail newspaper polls 1,000 Canadians, and based on this poll, says that 68% of Canadians want something. Now, did the Globe and Mail measure all Canadians? No, they only measured the 1,000 ones here. And depending on whether or not they talked to them by phone or some other method, chances are pretty good they actually contacted a lot more people before they found 1,000 people willing to talk to them. So basically, we've got the fact that this is an estimate. An estimate of the 1,000 Canadians based on the sample. Now, if the Globe and Mail truly wanted to find out what the deal was with all Canadians, they'd have to actually track down every Canadian and ask, and often we don't have the resources for that, or my shorthand is that we're too lazy, or we don't care enough, or it's too expensive, we're too cheap. The idea is how do you deal with the fact that you're trying to make a statement about the entire population, but all you've got is a sample. Okay, so let's take a look. I should mention that statistical inference also makes decisions about populations based on samples, but that's beyond the scope of this course. So let's take a look at an example. Okay, why is this thing not scrolling? There we go. Okay. I do not know what it's doing. So for example, you measure a sample of 5-year-old Douglas fir trees. There's like a tree farm or something like that, or a place that was logged and newly planted, and you find that the mean diameter of these fir trees is 55 centimeters. Now, I should make it clear that I made up that number. I have no idea how big Douglas fir trees are in diameter when they're 5 years old, but I just plunked down a number for reference. So we can talk about it. So what can you say about the entire population of 5-year-old Douglas fir trees? You could say 5-year-old Douglas fir trees in BC or on Vancouver Island or something like that, but clearly trying to measure actually every single 5-year-old Douglas fir tree would be a bit of a proposition. It would be quite difficult. So generally we would take a sample. And if your sample is representative, we're going to assume that you've used good sampling techniques from here on in. We looked at sampling plans earlier and how to select a sample properly and that kind of thing. You can estimate that the mean diameter of all 5-year-old Douglas fir trees is about 55 centimeters. That the average of your sample or the mean of your sample is going to be the mean of the population. But did you get it bang on? That's actually kind of unlikely. What does about 55 centimeters actually mean? Could it be that you mean 55 plus or minus 1, that you're actually pretty confident that you did a really good job and you're within a centimeter of the true value? Or do you think you're probably within 5 centimeters true value because there's a lot of variability in your sample, or you didn't take that many samples or something like that? Now, the terminology that I've used here is 55. That's the central value plus or minus. So that's a plus or minus sign, plus or minus 1 centimeter. Another way to write that is to say that that is from 84 to 86 centimeters. In other words, I took my central value of 55 and subtracted 1 to get the lower value and added 1 to get the upper value. 55 plus, 55 plus or minus, oops, what am I doing? Apparently something I can't add. I'm looking at some old notes. This would be from 54 to 56 centimeters, and the bottom one would be from, still using 8 for some reason, from 50 centimeters to 60 centimeters. Now, just for a little bit of jargon, the plus or minus part is called the margin of error. And the way we've written it on the right-hand side, this is an interval. And so the whole point here is that when we have a sample and we try to generalize that to the population, because we didn't measure the entire population, our sample might be a little bit off. And so we try to account for that by giving a little bit of wiggle room, a little bit of margin of error, saying that our sample could be a little bit on the low side or a little bit on the high side because we didn't actually measure anybody. Now, a great question is, how do you actually calculate that margin of error? And we're going to learn how to do that in the remainder of the section. But before we go there, I wanted to make another point. Is it not also true that occasionally the sample may contain an outlier? Recall, an outlier is a value that is very high or very low, that's very far from the rest of the values. And it could be that even though you did your best in taking a good and representative sample, that by just sheer random fluctuation, you got an outlier. Occasionally, your sample is just going to be a little bit off from where it should be had things worked out better. And occasionally your sample will, due to random variation, not predict a population mean accurately. A good question you could say is, how do we handle this? We say something like, based on our sample, oh, I should fix these numbers down here. Based on our sample, we have determined that the mean diameter of 5-year-old Douglas fir trees is between 50 and 60 centimeters. So that's our interval here with 95% confidence. So we're not 100% confident that that's actually the true value because we didn't measure everything. But we did a pretty good job, and we think that 95% of the time that we will have captured the true value. So when we talk about a confidence interval, and we say something like, the average temperature in Victoria at noon yesterday was between 12 degrees centigrade Celsius and 16 degrees Celsius with 90% confidence, we didn't actually measure the temperature in Victoria everywhere. We probably went to a certain number of sites within Victoria that constantly measure the time or measure the temperature. There's generally temperature sensing down in the Inner Harbour and out at the airport and at various other places around Victoria. And so we took a number of different readings, and based on that, we have come up with an interval between 12 degrees Celsius and 16 degrees Celsius. But what does the 90% mean? It means that we calculated that interval using a method that gives correct results 90% of the time. In other words, 9 times out of 10, the true value will fall within that interval, and 1 time out of 10, the prediction will be incorrect. If 90% is not good enough, then you need to step up your game and use a method that will give 95% confidence or 99% confidence. There's only one way to find it with 100% confidence, and that is to actually identically measure the entire population. And generally, we're reluctant to do that because that tends to be a pretty big deal. Now, for confidence intervals, this 90%, the most common confidence interval is a 95% confidence interval. And if we look at our little picture here, that basically says we've got a symmetric interval around the mean, and using z-scores here, the shaded interval has area as 0.95. And a good question is, what z is that? Well, we're using an online calculator from the Hyperstat online textbook. I'll put a link in the description. And if we take a screenshot of that, we use the second option, we're using the value from an area used to compute Z for confidence intervals. We've said that our area that we want is 0.95, so for 95%. And because we want to calculate Z-scores, we're using a mean of 0 and a standard deviation of 1. And then the result down here is our answer. And you can see that our Z is 1.96. Now, this should be a pretty familiar result because the empirical rule says about 95% is within 2 standard deviations of the mean. And if you want to know exactly 95%, then it's just a little bit less than that. So other common confidence intervals, I've got a little table here. Other common confidence intervals are 90%, 98%, 99%, and they also have Z-scores associated with them. So if you were to plunk this into the online calculator and do exactly the same analysis that we did above, you'd calculate Z-score if you were using a 90% confidence interval. Your associated Z is 1.645, 95% is 1.96, and so on. Now don't use 2 from the empirical rule because 2 is just an estimate and 1.96 is far more accurate. Now, any other confidence intervals? Oh, there's some notes from last time. If you're using any other confidence intervals like 92%, 96%, or something like that, then just use the online calculator to find Z. So we've talked a lot about what a confidence interval is. Let's talk about how you actually construct one of these guys. So to construct a confidence interval, you need the following pieces of information. You need, well, the confidence level. For example, you've decided that you want a 95%, and you can look up the Z-score that goes along with that. You're also going to need the sample mean. So you took your sample and you've analyzed it and you now know what the mean is. You also need the standard deviation. Now generally you don't have the standard deviation of a population. So for very large samples, and that's all we're doing in this class, you can just use S, where S is the standard deviation of the sample instead. It gets more complicated when you have small samples, but we're going to assume large samples for the purposes of this course. And if you want to get into the weeds, then you can take a full statistics course and learn about that. And we also need the sample size N. So here are the pieces of information we need. We need the confidence level, we need the sample mean, the sample standard deviation, and the sample size. For the techniques we're learning, we're doing large samples, and so we have to have at least 30 samples in our little group in order to be able to declare something about the population. Okay, if you have those pieces of information, then you plug it into the following formula. Remember that mu here is the population mean. That's the thing we're trying to estimate. That's going to be equal to the sample mean, and then this entire, let me use a different color pen here. This entire term that I'm highlighting, this is the margin of error. So let's make a note of that. The entire term is the margin of error. We call it MOE. And you replace sigma in there with the sample standard deviation S, provided, of course, that your sample size is large. We're only using large samples here. So basically, you take this equation, you plug all of your values into the right-hand side, and that will give you your population mean that you're estimating. in our next and final video, we'll do a full example of this.